Today we have with us Patricia Schuster, who's a graduate student in the Nuclear Engineering Department at UC Berkeley, and working with Sandia National Laboratories as a part of her doctoral thesis. Patricia is going to be graduating in May, and so we're really excited to have her here today to talk about her thesis research. Today, Patricia is going to be talking about the directional dependence of scintillation in organic crystals. Patricia.
Hi, everyone. It's me, Patricia. Right, so thanks so much for logging in to see this webinar. It's really exciting to do this. We have a few people here at the NSSC suite, but we'll be making sure to keep track of all the questions that you write in the little chat window. So if you have any questions, just send a little message and Bethany will be watching. Right, so as Bethany says, I'm a PhD student in the Nuclear Engineering Department, and I'm finishing my PhD this May. I'm currently looking for job opportunities, and this is my thesis research investigating the directional dependence in organic crystal scintillator materials. So these organic scintillators are used for a broad range of radiation detection applications. And here I'm showing a picture of a still beam crystal scintillator, that's the little rectangular prism there, on the face of a photomultiplier tube. So the way the radiation detection occurs is radiation deposits energy in the still beam material, and then that energy, a fraction of the energy produces molecular excitations, a fraction of those excitations de-excite by light emission, and then that light is converted into an electronic pulse. So as I mentioned, these are used for numerous applications in nuclear security and in basic science. And these materials can be used as liquids, plastics, or crystals, and they're very nice to work with, especially for this property in which they can tell the difference between neutron and gamma ray events based on the pulse shape. And I'll go into detail on how that's done and why that is possible. So the crystal scintillators are especially nice to work with because they're in their solid physical form, which is very convenient for portability, especially when compared to the liquid materials, which can crack and spill, and by the way, they're toxic, so they're kind of dangerous to work with. There's also a new recipe for producing still beam developed at Lawrence Livermore National Laboratory that produces large-size materials with excellent performance. So there's a lot of interest in still beam right now. But there's this directional dependence in the neutron interactions, and that is what I will be exploring today. So first I'm going to start with some background information on organic scintillators and this pulse shape discrimination process. Then I'll talk about the light production processes and why there's a difference in the pulse shape. Then I'll talk about my measurements that I'm doing to characterize the directional dependence in these materials. Then the hypothesis for the physical mechanism that's producing this directional dependence. And lastly, discuss some applications for using the directional dependence or just the impact that it has on current existing systems. So starting with this pulse shape discrimination. So for those of you who don't work with scintillator detectors, the way the radiation detection occurs is the radiation deposits energy in the scintillator material, and there's a few different types of scintillators beyond organics. Through some physical mechanism, light is produced in response to these interactions, and then that light bounces around, and then it enters this photomultiplier tube that converts it to an electronic pulse, which is measured as the signal out. In organics, there's a few processes that can be measured. For neutrons, the most prevalent process is probably an elastic scatter interaction on a proton, which is the nucleus of the hydrogen. This produces a proton recoil in the material, and that proton goes on to have collisions with the electrons in the material. And because the proton is so much heavier than the electrons, it travels in a quasi-straight path. So it's populating excitations along a pretty straight path with a high DE/dx. So those excitations are pretty close together compared to from a gamma ray interaction. So gamma rays would deposit energy often by a Compton scatter interaction, which produces a recoil electron. So the electron recoils in the material similarly to the proton, except when it interacts with the other electrons in the material, it's the same mass as the target electron, so it suffers wide angle scattering. You can think about billiard balls. So it does not travel in a straight path, and also it deposits a lower DEDX, so the excitations are farther apart. What we observe is a difference in the pulse shape, and here I'm showing the pulse measured from a neutron event on anthracene. When I compare it to a gamma ray event measured on anthracene, normalized to the pulse height, you see that the neutron event has a larger relative amount of delayed light, has a longer tail. And this can be used to determine whether an event was from a neutron or gamma ray interaction. So this process is known as pulse shape discrimination. And a simple method is called the tail to total method. And in this, you calculate two things. The first is the pulse shape, which is the fraction of light in the delayed region of the pulse. So for neutrons, that pulse shape will be higher. And then the total light output, which is an integral across the whole pulse, and that's basically your energy measurement. If you measure a large distribution of neutrons and gammas and produce a two-dimensional distribution of the pulse shape versus the light output, you see something like this, where the upper band is populated by neutron events that produce proton recoils. So as we saw on the left, the neutron event had a larger tail, so a larger pulse shape, so it's higher. And then the gamma events have a lower pulse shape, so they're lower. And basically, the performance as a PSD detector depends on how well you can resolve the two distributions. If there's a really good separation between the two, then it's better. You can say with greater certainty, like, I know that this is a neutron. If the two distributions are closer together or they overlap, then you have less certainty in making that conclusion. And so to quantify that decision, we have to assign sort of a number to the performance in pulse shape discrimination. And so one way to do that is you pick an energy range. Here I'm picking, I think, 3,500 to 4,000. And then you take all the events in that energy range and you make a distribution of their pulse shapes. So basically, it's like a slice, and you're looking at it like a histogram, just along the energy slice. And you have, in this one, the lower pulse shape values are the gamma rays and the higher ones are the neutrons. And then you calculate a figure of merit, which is the difference in the means of those two peaks divided by their full width half maxes in quadrature. This is kind of difficult to see, but basically the plastic PSD is the worst, then anthracene, and then liquid is better than anthracene. So for a long time, liquid was like the preferred material because it performed the best, but now these still being materials are better than all of them. So they're outperforming on pulse shape discrimination, and they're really nice because they're solid. And so really there's a huge effort to work with still being materials. So now I want to explain, based on the chemistry and the light production, why there's a difference in the pulse shape. So the excitations that produce light are the excitations within the pi orbitals. And these are, there's several different types of orbitals in these materials. For instance, the black line that's connecting, the sides of the hexagon there on this benzene molecule, that's a sigma bond connecting two carbons. And then there's like an extra electron in the pi orbital that's not bonded. And so the pi orbitals go above and below the benzene ring. And they actually bond with each other in a way and delocalize so that you have like these pi orbitals that share the electrons across the entire molecule. And what that does is it lowers the energy of this bond so that when the light is emitted, it's the right energy to produce an optical photon. And so that's why we see light emitted from these excitations and not from other molecular orbitals. So these are the molecular structures for anthracene and stilbene. And you can see they're quite different. They're both based on the benzene ring. And in fact, all of these organic scintillators are based on the benzene ring. So basically what's different about these is like anthracene, the pi orbitals will be conjugated across the entire molecule. So it will be like a giant oval orbital, whereas stilbene, because it has that little bridge between the two benzene rings, the wave functions will be centered more around the ends of the molecule. and it will be more difficult than an anthracene for electrons to move from one side to the other. Right. So if we look at the energy levels within these orbitals, so this is called a Jablonski diagram, and basically the left column are singlet energy states, and what that means is that the two electrons, which are indicated by the little arrows, have opposite spin, so the total spin of the system is 0. And the S0 is the ground state. S1 is the singlet excited state, and T1 is the triplet excited state in which that valence electron flips its spin. And when it flips its spin, it just makes it more difficult to transition back to ground state because it has to reverse its spin in that transition. But without going into too much detail, there's lots and lots of different processes that can occur in here. And the little lines, the sort of skinnier lines, are vibrational excitation levels. So the solid lines are like the electronic excitations. But we're not going to worry too much about the vibrational levels. In fact, we're just going to simplify it to a system like this. So on a very short time scale, these excitations produced by the radiation will simplify down to a system of singlet and triplet first excited states like this. So you'll have, still a lot of ground state molecules that were never excited, and then a bunch of singlets and triplets moving around. And these can produce light. So the singlets will produce light through fluorescence, which occurs on a very short time scale. And triplets can produce light through phosphorescence. And the delay there is because the valence electron has to reverse its spin. So it's just much less likely and occurs on a much longer time scale. So what that means to us is that if you look at a time distribution of light produced by these things, the phosphorescence is so slow that actually we don't observe it because my measurement system is only about 200 nanoseconds long. So we just removed that from the picture totally. But there are ways to observe the triplet light. And one way is called triplet-triplet annihilation. And in this process, two triplet states interact and annihilate into a singlet excited state and a singlet ground state. And then that singlet excited state can then decay by fluorescence, as it would have if it were born as a singlet state to begin with. So what this does is it contributes fluorescent light to the delayed timescales. And the delay depends on how long it takes for those two triplets to migrate and reach each other. So if the density of triplet states in the material is higher, then you'll have a greater rate of triplet-triplet annihilation. And like I've drawn this little arrow there. So as the density increases, the amount of delayed light increases. Another process that affects the light production is called singlet ionization quenching. And this actually works against light production. So two singlet states that are born at the beginning of the population or are close enough together to interact can quench one of them, and they super excite one of the singlets and leave the other in ground state. And then the super excited singlet can go on to produce light, but you could have had two light productions and you only have one. So what this does is it quenches the amount of light in the beginning. So if you look at the beginning of the pulse, there's an arrow going down because it brings down the amount of prompt light. So if we consider the differences between neutrons and gamma rays, neutrons produce a much higher DEDX, so the excitations are closer together. So you're going to have more of processes 3 and 4. So you're going to have more delayed light, less prompt light, and so you'll have an overall increase in the pulse shape, because the pulse shape is the fraction of light in the delayed region, and you've inflated the delayed light and you've quenched the prompt light, right? So really that's why there's a difference in pulse shape. The question is there a difference between neutron interactions at different directions? And we observe a difference that I'm about to show you how I characterize, and the question is really how is that difference produced? So now moving on to the measurements that I've made to characterize the directional dependence. I'll start with neutron measurements. So this is the same distribution I showed you before, just now it's a simple 2D scatter plot. And this was taken, the little star is my source, and the little cylinder is my detector. If I change the direction of my detector with respect to the source, I see a very different distribution. So there's a change in the light output at the endpoint and in the pulse shape at that endpoint. So something about now this direction of the interaction is producing more light and a different amount of light in the delayed region. Interestingly, you don't see a significant change in the gamma ray band. So really, at this point, it looks like it only affects neutron interaction. So I built a system to characterize this. And what I need to do is I need to measure proton recoils at a given energy in a controlled direction in a hemisphere worth of directions, because traveling in the forward and backward direction is the same within a crystal, so I only need to characterize one hemisphere. So to do this, I use only the full energy events from the neutron generator. So I'm controlling the proton energy and the direction, because the full energy events will send the proton in the forward direction. Okay, and then I can change the direction of my detector with respect to the source to probe different directions. And I have this beautiful system to do this that has two axes of rotation. The vertical axis is the kebab axis, and the arm is the rotisserie chicken axis. And using this, I can position the system at 4 pi worth of angles, but in the end, I only measure 2 pi. And then I can represent these angles in 2D. And this distribution is all those angles in the top hemisphere viewed in 2 dimensions as if you're above the hemisphere looking down and you've flattened it. And so you'll see this plot again as a contour plot, and the colors will indicate the value of the measurement at each angle in a minute. All right, so to calculate the light output and pulse shape of the full energy event, first of all, I only use the neutron events above a certain energy threshold. So this is another one of these pulse shape discrimination plots, and the red line indicates the cutoff. So I only use the neutron events that are above this line and to the right. And then I make a light output spectrum of those events, and I use a fitting function to locate the edge point on this distribution. So this is telling me the light output for a full energy interaction at this specific angle. So this is just for a measurement at one angle. Then I just use those edge events and calculate what's the average pulse shape for the events at the edge. So now I'm measuring the light output and the pulse shape for the full energy proton recoil events in a given direction. Right, and then I can plot them as a function of angle. So these are the same plots I was just describing. So the top plot is the light output measured at all these different proton recoil directions in the material. And the bottom plot is the pulse shape for those same measurements. So what you're seeing here is as the proton recoil changes direction in the material, or as you measure proton recoils at different directions, I should say, the light output varies from, it's starting at 8100 and going up to 9200, which is a significant change. So if you consider that you're trying to measure the energy of your interaction, like this is an effect that is affecting your energy measurement by introducing additional variability. And then the pulse shape on the bottom, we're seeing huge changes in the pulse shape, so that's going to affect how well you can resolve neutrons from gamma rays. So I don't know the crystal axes of my materials, but previous groups did. And so this measurement allows me to infer my crystal axes. And so I've labeled on here the A, B, and C prime axes, because Brooks and Sukata are previous groups who measured this back in the 60s and 70s. And they showed that the maximum light output occurred at the C prime axis and the minimum light output occurred along the B axis. One thing that you'll notice here is that there's a relationship between the light output and tail to total, right? So like if I draw these little lines just to guide your eye, the minimum in the light output corresponds to the maximum in the tail to total and vice versa. But then the saddle point in the distribution, which is where the A is in the tail to total and where the line crosses in the light output, those don't quite line up. So it seems like there's different physical mechanisms that produce, or that the physical mechanisms of the directional dependence impact the pulse shape and the light output in related but different ways. So just to quantify this, I'm just going to calculate the magnitude of change over this distribution. For a 14 MeV proton recoil, the light output changes by a factor of 1.155, and the pulse shape changes by a factor of almost 1.8. For a 2.5 MeV proton recoil, the light output changes by about 1.4, so you now have a larger change in the light output, but the pulse shape changes by a factor of about 1.3, so you have less change in the pulse shape. So both the light output and the pulse shape depend on the proton recoil energy, or the magnitude of change depends on the proton recoil energy. So there's really a lot of interesting things going on here, and this is just like a signature of the internal energy transfer mechanisms and light output production within there. And so we're getting this little glimpse into what's going on inside, and now we're going to try to say, like, okay, given this phenomenon, what can we say about how light is produced in these materials? So as I mentioned before, there is basically no directional dependence observed in gamma ray events, and many people have claimed this, but no one has measured it. And so I did a measurement with a cesium source. So this is the same anthracene crystal, same angles. I'm just measuring with a cesium source instead of a neutron to produce 478 keV electron recoils. And that just, it doesn't look like there's anything there. There's no smooth contours, there's no high and low regions. It really just looks like there's, you're measuring around a value with a certain error. And in the top plot especially, you see some outliers in the bright red and blue spots, and in the bottom, the bright red spot as well seems to be an outlier. Another thing to point out is that there's these little vertical bars on my color bar. Those are the statistical errors. So on the neutron plots, you see a very little vertical bar on the color bar. This thing. And in the tail to total distribution, it's so small, you can't even see it. But in the gamma ray measurements, the error compared to the magnitude of change is much larger. That's the point I'm trying to make. So the question is there a directional dependence in the gamma ray measurements? It really doesn't appear to be qualitatively, but the most we can say is to set an upper boundary on it, given these measurements. So to do that, so I'm going to say that the observed variability, which is the standard deviation in all these measurements, is the sum of any statistical error and any other effect that includes the anisotropy. And so for the neutron events, it really looks like this variability is due all to the anisotropy. And then from the gamma rays, it looks like there's not an anisotropy there, but this serves to set an upper limit. Right, so from the proton events, the relative standard deviation contributed by the anisotropy for light output is 3.7%, and for pulse shape is 16.8%. And for electron events, that is for light output only 0.4%, and for pulse shape only 0.7%. So first of all, we say that we don't observe a directional dependence, but if there were one smaller than my system could measure, still the effect in gamma rays is like a tenth or less of that observed in the neutrons. It's always fun to try to prove or try to demonstrate that you're measuring nothing. It just, anyway, okay. So I showed this to the group at Livermore, and I got the suggestion, well, why don't you measure cosmic muon events? So the motivation for this is that we have protons that interact with high DEDX in a straight path, and they produce an anisotropy. And then we have electrons that interact with a low DEDX in a not straight path, and they do not produce an anisotropy. So which one is important? Is it the DEDX, or is the straightness of the path that's important for producing an anisotropy? So muons share a characteristic with each one. They travel with a low DEDX in a straight path. So whether or not there's an anisotropy measured in muons will inform us about which one is more important for producing this effect. What's tricky about muons is they interact by depositing constant energy per path length. And so that means that the light output distribution is actually just the path length distribution. So, the distribution of cross sections through my material times this constant of energy per distance deposited. So if there were a light output anisotropy, the entire light output district would be shifted by a factor. because there would be a different amount of energy deposited per distance. But this constrains the angles that I can measure because I have to keep the same path length distribution. So the system that I'm using is shown here, and the little cylinder between those two blocks is my anthracene crystal. I can only measure at angles when the cylinder is on its side like this and I turn it along the height axis, because I need to keep the geometry of the whole system the same, so that like the way that I select muons is by selecting events that interact in all three detectors. So that constrains my measurement to only muons within that angle row. And I have to keep the path length distribution the same, so I have to keep the geometry of the system the same. So the only thing I can do to measure a different angle is to turn my crystal along its axis like this, so that the overall geometry of the system does not change. Does that make sense? Okay. So I'm measuring the light output and pulse shape at two angles that have significant difference in neutron events, but they're not the directions of max and min, because those are not along the sides. So I just want to make that clear. So what I've done is I measured muons at paths 1 and 2, and then I made a distribution of the light output spectrum. So on the left is the light output spectrum at path 1, and then on the right there is just looking at the peak feature and comparing the distribution at paths 1 and 2. So my question is the location of that peak feature significantly different between the two paths? And then this is a distribution of the pulse shape for events at that peak feature. And again, the question is the position of this distribution significantly different between the two? And in the end, I do not see a significant difference. So this is showing the results for neutrons at two different energies, the gamma ray measurements, and the muons at paths 1 and 2. So if you look at the L magnitude of change and S magnitude of change, there is a statistically significant difference in the neutron events, but not in the gamma ray or muon events. And so I conclude that I don't observe an anisotropy in cosmic muon events. And what that tells me about the physical mechanism is that the meandering electron produced by a gamma ray event is not solely responsible for the lack of anisotropy, because a muon is essentially an electron traveling in a straight path, and we don't see an anisotropy there. And this lends support to the theory that a high DEDX is required for producing an anisotropy. And there is anisotropy observed in alpha particles, which have even higher DEDX, so that's consistent with that as well. Right, so now I want to talk about measurements I've made across different materials, including other pure crystals and mixed crystals. So looking at crystals other than anthracene, I've measured numerous. I'll just show a few. So the first one is stilbene, which is sort of the material of interest right now. On the bottom here, I'm showing the magnitude of change in the light output and the pulse shape. And the light output changes by approximately the same factor, but the pulse shape anisotropy is much less. So in anthracene, it was 1.8. In stilbene, it's 1.08. So if you are trying to not have an anisotropy effect, then actually stilbene may be a better material for you. If you're trying to exploit an anisotropy, then anthracene might be a better material for you, although no one manufactures it, so best of luck. And then the last material here is p-terphenyl, and the light output anisotropy is, again, on the same magnitude, and the pulse shape anisotropy is on the same order as stilbene. So what's more interesting about these three is that the relationship between the light output and pulse shape anisotropy is different in all three. So if we look in anthracene, we saw that the minimum and the maximum are opposite in the two, they're out of sync. But then the saddle point in the distribution is at approximately the same location. Right, so the direction that produces the maximum light output produces the lowest pulse shape. Okay, but then in stilbene, the three features are all in sync. So now the relationship between light output and pulse shape is kind of opposite. But then in p-terphenyl, they're all out of sync. So the max is the min is the saddle point, and the saddle point is the max. So what is it about these three different materials that changes the relationship between the light output and pulse shape? That's really the big question to answer. I don't have an answer, so I'll just, break the news to you now. But hopefully, a lot of my results will inform that information. Right. So then, if we look at mixed crystals, This is another really interesting thing. So right now, the group at Livermore is also investigating, can we get the best properties if we make a solution of two different materials and then crystallize it? One example is combining stilbene. This is the same plot of stilbene that I showed you before, and this is an image along, I think along the A-axis, I don't know which axis, of stilbene. So an image of the crystal structure of stilbene. And then if we compare that to bibenzyl, the crystal structure is very different. And also the relationship between the light output and pulse shape is very different. We actually have a fourth behavior where the region of maximum light output in bibenzyl is along this contour between the high and low region in the pulse shape. So that's nice. If we combine these in a new material that is mostly bibenzyl with a very small component of stilbene, so bibenzyl with dilute stilbene, there's no pulse shape discrimination anymore. Even though the two materials on their own had pulse shape discrimination, there's no pulse shape discrimination. The pulse shape between neutrons and gammas is now the same. And there's no directional dependence as well. And these are measurements that I've made. I just didn't put them on here. Because again, it's hard to show that something is not there. Okay. But then if we change the composition and we make a material that's half and half bibenzyl stilbene, we get the PSD back, and we now have a directional dependence. So these are the plots, and you can see that, well, first I should say that there's a lot of questions about how these materials crystallize. It's not clear if one is an interstitial in the other, or which material is the primary scintillating agent. This shows that the directional dependence has the same behavior as pure stilbene. So does that tell us that stilbene is the dominant component? Maybe not, because if we look at the magnitude of change in the pulse shape, it's actually closer to that of bibenzyl. So there's a lot of interesting behavior going on here. So lastly, I just want to touch on the hypothesis for this mechanism. What is responsible for the effect? I've mentioned that these materials all have different crystal structure, which will impact the transitions and energy transfer. So spacing, orientation of the molecules. And then there's the question, could there be a directionally dependent DEDX? So as the proton recoil direction changes, is it depositing a different amount of energy per distance? You can think about channeling effects, where if it just happens to go into a range, where it's in this nice little window between molecules, maybe it can travel farther. And then there's also molecular structure. There's the degree of conjugation across the molecule, which means whether the pi orbital is delocalized across the entire molecule, or whether it's separated onto different regions. There's the energy levels of the excitations and the spatial extent of the wave functions, and all of these come together to give you different likelihoods of all of those light output processes happening. So how easy is it for an excitation to move to a neighboring molecule? That depends on the distance and their orientations and all that. How easy is it for two triplets to annihilate into a singlet excited in ground state? Well, if the energy of the two triplets is about half of that of the singlet, that is pretty perfect. Right, so another idea is that there are preferred directions of excitation transport, and this has been demonstrated in a number of organic scintillators. So if you populate along a direction with easy transport, then your excitations will travel within that direction, and the density will remain high over their lifetime. But if you populate your excitations along a direction with difficult transport, then your excitations are more likely to move away from the trajectory. And so you'll have a lower density over time. And if you remember back to the light output slide, the amount of the triplet annihilation and singlet ionization quenching depends on the excitation density. So if your density is changing in different ways in different directions, then you'll see different light output in different directions. And for these two situations, what you would see is in the yellow distribution compared to the blue one, the yellow one has a lower density over time, so you'll see less of those interactive processes. So you'll have a higher amount of prompt light because it wasn't quenched as much, and you'll see less delayed light because there wasn't as much triplet annihilation. Another complication is that the triplets and singlets don't necessarily have the same directions of preferred excitation. So that could, or preferred transport. So that could be a reason why the relationship between the light output and pulse shape is different in different materials. If they have opposite directions, or one of them is like a third direction within the material. You know, there's a lot of things that could be going on. All right. Lastly, to discuss applications and impacts. So if you already have a system that uses like liquid scintillator and you want to now use these still beam crystals, how does this impact your system? Well, the first thing is that compared to a measurement at a fixed direction, if you have neutrons going at a lot of different directions, this effect will degrade your energy resolution and it widens your pulse shape distribution. So one question is it possible to correct for the effect and get improved performance? Or if you're making a controlled measurement, can you just position the source at the angle that's best for energy resolution and PSD? That's an option too. What I'm really interested in is trying to understand the effect. What properties of the material dictate the anisotropy? Can those properties be controlled, or can they be exploited in order to produce new materials? The new materials could eliminate the effect or enhance it according to one's needs. And also, this type of investigation just contributes to the body of knowledge around the physical chemistry of these materials, and that information would benefit similar materials like organic photovoltaics and organic light-emitting diodes. So in solar cells, which use photovoltaics, you know, a big effort right now is to increase the efficiency, so the conversion efficiency. You have a certain amount of energy going in, and you're trying to measure as much light out as possible, or, you know, convert as much light into electricity as possible. If you can harvest your excitations more effectively, then you will increase the efficiency. So maybe something about these materials can inform that industry. Lastly, can you use this effect? One application that is always proposed is to employ the effect in a compact directional detector with high efficiency. So if you've seen the existing neutron imaging systems, they're often like several detectors, like 16 or 32 detectors with everyone has a wire and a cable, and you're trying to synchronize all the signals and you require several interactions. Or you have like a shield in front of your system with little holes in it, like the coated aperture, and so you're blocking half of your signal. But these materials have the directionality all inherent to the physical structure, and so you wouldn't have to block any of your signature. And so that makes it higher efficiency. Also, it would be a single channel with relatively easy electronics, and it would be hand carryable, which is really nice for first responders or someone walking around with the system. And it's also been proposed for dark matter detection. And the way this would work is basically you set up your detector stationary on Earth, and as the Earth moves with respect to the universe, you will see different signatures as a function of the direction of your detector with respect to the dark matter. And so then you can say, like, I think there is dark matter, and I'm measuring it, and it makes sense considering the angle of my detector system, you know, that kind of stuff. So that's a really interesting application. So in conclusion, this directional dependence is significant and it's complex. It's really interesting. There is a variation in magnitude and behavior across materials, and the directional dependence affects the energy resolution and pulse shape discrimination when using these materials. So these really offer the potential to learn more about these systems, because ultimately what it is an interesting signature of the internal energy transfer processes. So can we use this to learn about these materials and improve future materials? And also, can we apply the effect as a directional detector system? So I'd really like to say thank you to Bethany and Erica for inviting me to do this. It's been really enjoyable, especially for Erica. She's not here today, but she's possibly the most organized person I've ever met, and she made this very seamless. I'd also like to say thank you to my group at Sandia for hosting me for the last 5 years for doing this thesis project. It's been a really nice experience to work with them.